All right, so you know the drill. By watching this, and remind me if I don't give you your 10 extra credit points, good for missed assignment points. So anyway, let's see what slides would be significant for your Unit 4 exam. It's not made up yet, but I've got some ideas. So this slide says a lot of different things about water. So for instance, ours is the only planet in the solar system to have water exist in all three phases. Water came from comets. Water on Earth came from comets, we think. About 70% of the Earth's surface is covered with large bodies of water. There's more water in the northern hemisphere. Sorry, there's more land in the northern hemisphere and more water in the southern hemisphere. Large bodies of water. Water can vary from 0 to 4% by location and day to day, and that most of Earth's fresh water is tied up at the poles. Then we've spent some time this semester talking about solid, liquid, and gas. And when we talk about especially kind of what water does in the atmosphere, whether water is a gas, whether water is a liquid or a solid, we need to be able to talk about these physical phases. Remember that the gases have a lot of kinetic energy, solids not much, liquids in between. So the length of the arrow means like how much motion they have, and with motion they have kinetic energy. So let's see if I have this on here. The other thing is, well, yeah, maybe it's coming up. Yeah, it's coming up. So water actually has these, what we call intermolecular bonds here. These special types of intermolecular bonding called hydrogen bonds. The reason they're called hydrogen bonds is because remember the white atom here on a water molecule is a hydrogen. It actually is drawn to an oxygen atom of another water molecule because it is oxygen, hydrogen. The hydrogens are partially positive, and the oxygen is partially negative. So that's why if this is another water molecule, this partially negative part, that is my intermolecular bond right there. Partially positive hydrogen. Okay, so hydrogen bonds are the things that keep water particles together, whether they are a solid or a liquid. Remember, gases basically have no intermolecular bonds, no hydrogen bonds. So speaking of phase changes, we have this solid liquid gas thing going on, and we know that actually we have to add energy. So energy up means energy in. So we are adding energy here. Okay, and here when gas condenses or when liquid freezes, actually energy is released. So kind of know that we have, the names for the different physical phase changes. If something goes directly from a solid to a gas, we call that sublimation. Directly from a gas to a solid, we call that deposition. And all of these phase changes, whether you need to put heat in or whether heat is released, those are all called latent heats. Latent heat is the energy associated with a phase change. And then we talked about the water cycle. So just kind of generally know, evaporation, condensation, precipitation. Let's see what else do I have. Yep. Cloud condensation, nuclei. Wonder if that didn't get on there. Hopefully it's coming up. Let's see. This is what I thought was going to be cloud condensation nuclei. Yeah, don't worry about this one. I don't think there's a whole lot on here. I really like this figure because this talks about there's no water here. If we give it time, remember the water, you can see the water vapor increasing. We see water vapor particles here, a little bit of condensation. And here, this is actually at a place that we call equilibrium. The air over here is saturated. We have evaporation and condensation, but it's going on at equal rates. Okay. Let's see. Most people are familiar with, I don't think you need to know this slide because I don't have anything on there about those types of humidity. So don't worry about this slide. Worry about this slide though. I notice there'll be a question about relative humidity, and actually that's the one that we're most familiar with. The M stands for maximum content, M maximum content. This actually is the max, these are MC values, maximum content. Okay, so these values, notice that we said that warm air holds more water vapor than cold air. Okay, so up here you're looking at 0.1 grams of water per kilogram of dry air, and here you're talking about 47 grams of water vapor per kilogram of dry air. So warm air holds more water vapor. So these things are actually going to be from the table you're going to put in for your maximum amount of water vapor. And then we said that actually if your actual is near your maximum, then you're going to push 100% relative humidity. And the closer you are to 100% relative humidity, the more likely for condensation to occur. And there'll be one of these on the test. I don't know if it's this figure or we had another figure too, but remember we actually calculated relative humidity by doing the actual content over the maximum content. From the maximum content we got from the table on the previous slide. Okay, so we might want to take a look at that. There'll be a question about heat index. Remember how that works is this is actually what the thermometer says, and this is this is the relative percent humidity, and the more humid it is, the hotter it feels to us. So if we were to pick a day where our thermometer said 88, but we're running 80% relative humidity, where they cross, wow, that means we would feel it, the feels like temperature would be 106. And remember why the feels like temperature does it. It has to do with actually our sweat does not evaporate, and that evaporation makes us cooler. Okay, so clouds actually, I'm going to put it on this slide. Cloud condensation nuclei. Cloud condensation nuclei. Now, you can go ahead and get a chunk of air to cool down, a chunk of air with just water vapor. And if you get that chunk of air with water vapor to cool down, if it's got these cloud condensation nuclei, abbreviated CCN, those are what water forms around. Okay, so this is liquid water forms around these. Okay, and the liquid water then is actually the cloud droplets, or the beginning of a cloud droplet. So how do we get a chunk of air to go up? Well, there are 4 actually ways to get a chunk of air to rise. And if you can get a chunk of air to rise that's moist, then you can get condensation, maybe precipitation. Let's take a look at that. No, there's nothing about, looks like lifting condensation level. Okay. So these actually, all of these are starting out as snow. And we talked in lecture that actually it kind of depends on what your temperature is like going down. So if your temperature stays cold, then it's going to land as snow. But if your temperature gets warmer, then it's going to melt and become rain. Now we have a couple of options over here. And in both of these, it's cold, okay, gets warm and gets cold again. Cold, warm, and cold. And this warm melts it, and this cold actually, if there's enough room, will refreeze it into pellets we call sleet. If there's not much room, it will freeze on things we call freezing rain or glaze. So kind of know those. Of course, know the 10 cloud types. We break the cloud types with regard to low, they have no prefix. Middle clouds have an alto prefix, and high clouds have a cirro or cirrus prefix. And then we break them up into fluffy or layered. So know those 10 types of clouds. Air masses and weather fronts. We end up with these 5 different types of, maybe it's coming up on, these are, I wonder if I guess, yeah. These aren't the 5 types of air masses. These are the things that go together to make the 5 types of air masses. Here we have moisture content, and here we have temperature. So this is moisture, and this is capital T for temperature, or temp. I better put T for temp. Okay, and we kind of mix and match those and get these. I ended up with 6. Okay, actually, maritime Arctic is not very probable. But so know those different types of air masses. So these are the air masses, and these are what we call the source regions. And source region is just where a water can pick up, excuse me, air. Air can hang over there for a couple of weeks and pick up either being dry or being wet or being cold or being warm. So know that. Weather fronts. Cold fronts would be blue with triangles. Warm fronts would be red with semicircles. Stationary fronts would be blue and red with alternating blue, red, so triangle, semicircle, triangle, semicircle. And occluded fronts would generally be purple. And remember, what makes these two what they are is what air mass is being aggressive. Question mark aggressive. Okay, oops. Goodness, oh well. I can't spell, but you know what I mean. Which one's being aggressive? It's the blue air, excuse me. If it's the cold air that's moving in on the warm air, then it's cold front. Warm air moving in on cold air, it's cold front. Stationary front, not moving either way. An occluded front has to actually do with 3 air masses. All right, let's see what you need to know about for part 3. So I have one here about aerosols. Okay, so aerosols are suspended liquid or solid particles, and they make great cloud condensation nuclei, and they have other effects too. Permanent versus variable gases. Permanent gases are listed here. Most abundant permanent gas is nitrogen and oxygen, about 80-20, and then we've got kind of these trace gases. Permanent means that that's generally in this constant with regard to concentration. Variable gases means their concentration varies from day to day, location to location. 3 main variable gases: water, carbon dioxide, and ozone. Question on there about why skies are blue, and it has to do, it's called Rayleigh scattering, Rayleigh scattering, and it has to do with actually nitrogen and oxygen in the Earth's atmosphere that selectively scatters. If we have Roy, G, Biv coming from the sun, these blue, indigo, violet are going to be scattered the most, and that's why the skies appear that color. And this is the same reason that when the sun is low on the horizon at sunrise or sunset, notice that it's all scattered out. So what finally gets to us is just kind of these long wavelength colors. We talked about 2 trends of carbon dioxide. Notice that these are years going across along the x-axis here, and we blew one of these up, I think we did anyway, and it peaks. It has a peak and a trough for each year, and what the peak is and the trough is has to do with plant activity. So that's the yearly trend, but the other thing is, can you kind of see this upward trend from year to year to year of carbon dioxide? And that's what we're definitely not it's not a good thing. Right now we're actually above 400 parts per million, which is not good. So this actually trend has to do with, like this says, human activities, burning fossil fuels, and deforestation. The greenhouse effect, generally speaking, the way our atmosphere is kind of like a greenhouse is you kind of have to figure the greenhouse itself kind of traps. Can you kind of see it trapping this red wiggle mark? This red wiggle mark is heat. Okay, so what happens to a greenhouse, within a greenhouse and within the Earth's atmosphere, is we can get a shorter wavelength from the sun warming up the Earth, in this case warming up some plants in a greenhouse, and then in the greenhouse it can't get past the glass. In the Earth's atmosphere, it actually bangs around and hits the greenhouse gas particles like carbon dioxide, and it acts like a blanket to keep the Earth warm. Ozone. Actually, there is good ozone. Good ozone, and this is a layer of ozone in the stratosphere. Bad ozone is actually in the troposphere. So I have a slide coming up. You're going to want to know kind of what the layers of the Earth's atmosphere are, but the one closest to the Earth's surface is troposphere, followed by the stratosphere. I think I'm going to have a question on there about the ozone hole. The ozone hole is actually formed over the poles. In the ozone layer in the stratosphere, the good ozone actually has a hole in it seasonally. about springtime for both hemispheres. The Arctic, which this is the Arctic, so this is the southern hemisphere. They're looking down here at the North Pole. Actually, the hole is more predominant, and it has to do with chlorofluorocarbons in the Earth's atmosphere that are released in the springtime. These are the layers of the Earth's atmosphere. This is the Earth surface going up. The other thing I guess I would point out is that within the troposphere, as we go up, we get cooler. Oh, that wasn't right. Goodness gracious, look at this. The troposphere actually is, that didn't work. If this is the Earth's surface, we have the troposphere, and then above the troposphere, we have the stratosphere. I think I put this up on a board. And then above the stratosphere, we have the mesosphere. And above the mesosphere, goodness, we have the troposphere. So also generally know what the trend is going up in that layer of the Earth's atmosphere. And then the last one for this part was what happens, and you guys know this, if you climb a mountain, you know, the air gets thinner. And the air gets thinner, you'll have less oxygen, you'll have less nitrogen and all that too. And so actually the gas pressure, so P for pressure, is less as you go up. So be able to explain that. When we have a change in pressure, and actually this is coming up in the next part, a change in anything we call gradient. So a change in pressure, we call it pressure gradient. So here we have pressure is less, so I'll put an L up here. Pressure is higher down here. You can almost see that, isn't it? I'll put an H there. So that's actually an example of we call that a vertical pressure gradient. All right. So on to the next part. How do we get, now we're changed, that was vertical, switching gears to horizontal. So horizontal would be flat across the Earth's surface, not going up. So how do we get differences in pressures? One is temperature, and as it turns out, actually warm air has a low pressure, cold air has a high pressure. It could be moisture, and this is kind of counterintuitive. If it's a moist air mass, it's actually going to be low pressure. If it's dry, it's going to be high pressure. Dry, high, get it? I don't know. If air is on the move, if it's meeting up in one place, that will create a high pressure. So here we have a convergence zone. Remember, we're throwing candy up in a crowded on a crowded playground. Okay, the kids are going to converge and make a high pressure, and then someone's going to throw up, and they're going to diverge and create a low pressure. So those are 3 different ways we can get a difference in pressures on the surface of the Earth. So differences in pressures are important because the next slide actually I think says actually differences in pressures are what makes wind. But we did this exercise kind of in lab, I think, where these lines mark equal, for instance, I've circled the 1024 millibars. All locations here have 1024 millibars pressure. All locations here have 1020, 1032, 1036, okay, 996, okay. And then the other thing is, if you look at it, you should be able to tell that this is actually a central low. Why? Because it's low, it's a central low, and it's getting higher. So as we go up as we go out from the bullseye, we are getting higher pressures, and so this must be a low. The opposite is true here, because so as we go out from this, we're actually getting lower pressures. So that's what makes this a central high. So those are isobars. So what creates wind in the first place? So wind is air just relocating from a high to a low pressure. And so these things that look like kind of football field lines, yard lines, those are isobars. And so can you see where we have the 992 millibars, 1016 millibars? But like, for instance, where this is spaced, this is actually, the big spacing makes it a weak pressure change, a weak pressure gradient. These are these closely spaced isobars. Okay, that's a strong pressure gradient, and it will give you strong winds. Weak one will give you wimpy winds. Okay. The second feels like temperature actually has to do with the wind, not the humidity. And so, know why that happens. And I think I kind of drew my picture as a picture of my hand. We actually have around all, we're warm-blooded animals. This is my kind of heat, my heat shield that I created from my internal thermal energy. And so if we have wind blowing on us, that wind is going to take our heat shield away and we're going to feel colder than usual. No wind and we're going to feel warmer than usual. So the way this works is, let's see, how does this work? This would be your thermometer temperature. Let's just say we're running 10 degrees Fahrenheit. Not bad. Okay, but if the wind is blowing on us at 35 miles per hour, that feels like temperature instead of 10. It's going to feel like it's negative 14. Yowza. Here's one for you. The Earth, what you're looking at is looking down at the North Pole here, and the Earth obviously is spinning counterclockwise, right? And so here's the deal. If a plane heads towards A, the Earth is going to rotate, and it's going to actually end up appearing to go towards B. Now here on Earth, we have this apparent deflection to the right in the northern hemisphere. It's in here, yeah, to the right in the northern hemisphere, to the left in the southern hemisphere. And so large bodies of air and large bodies of water have this phenomenon as the Earth, and Coriolis calls Coriolis force, and it's due to the spin or the rotation of the Earth. Then to kind of finish up, we might see, it won't say hi, I'll see just the letter H. This might be something you see on the weather map. That system we would call an anticyclone, and I want you to know a few things about that system. Anticyclone means it's going anti to how the Earth's rotating in our hemisphere. The Earth's rotating counterclockwise from the North Pole, so that's why the winds are going clockwise around, or the winds will be going clockwise around a high. The other thing, and we touched about this on lab, is your central high pressures will have clear skies and probably warm conditions. Wimpy pressure gradient, which means wimpy winds if at all. Then we'll contrast that to simply your central low pressure on the weather map. We call that a cyclone. Your wind will be going counterclockwise, just as the same rotation in the northern hemisphere. And that's where you might possibly have tight isobars, strong winds, cloudiness, cool conditions. Okay. So winds, there actually are 3 scales of winds. There's a microscale, mesoscale, and macro scale. And they differ by how big they are. You can kind of see how big they are along the x-axis here, and then how long they last. So know those, and I've got some examples here in this figure. Let's see. I'm going to pick this local or mesoscale wind to talk about. Remember that this is like a lake breeze, sort of, sea breeze, and remember, breeze or wind will only occur if you have some sort of high pressure going to low. And in this case, you can kind of see the squiggle up here is that's because trying to show you that the land is warmer. And I said that warm air has a low pressure compared to cool air. And so that's why during the day we get this sort of incoming breeze. And then at night, okay, the land cools down more quickly. So if it cools, cold air will have a high pressure. Yep. And warm air will have a low pressure, and so this is an outgoing breeze. Pair of local winds. You're going to want to know kind of your way around this idea of 3-cell, I call it 6-cell model. Of course, we have in each hemisphere a Hadley cell, a Ferrel cell, and a polar cell. And then we talked about how at the Earth's surface we have these trade winds that meet up from the North and the South Pole, and they meet up at the intertropical convergence zone. And then so these are easterly trades, and then we have a westerly wind as part of the Ferrel cell. Associated with the polar cell, we have another easterly wind. So they kind of alternate at the Earth's surface. And don't forget kind of where these cells break down. 0 to 30, 30 to 60, 60 to 90. Nice and symmetrical. Let's see. This is the wandering intertropical convergence zone. Not so surprising. In July, it wanders north. In January, it wanders south. July north, January south. Yeah, but it's our hot spot. Hot spot, some people would think, is the equator. Not necessarily. It's the intertropical convergence zone. And then I'll put an H here for Hadley. So actually, the intertropical convergence zone kind of separates the northern 3 cells and the southern 3 cells. So we talked about jet streams. Jet streams are a ribbon of fast moving air, and it may not always be this. I'm kind of showing it continuous. There might be breaks in it. There's some kind of neat stories about hot air balloons trying to catch the, counting on the jet stream being there, and it kind of peters out. But they're located between the major cells. So we have the polar jet between the Ferrel and the polar cell, and the subtropical jet between the Hadley and the Ferrel cell. And the jet streams will migrate with the cells that migrate with the intertropical convergence zone, which migrates with regard to the seasons. Speaking of, we talked about monsoons. Monsoons, actually, you'll have a pair of monsoon seasons, a wet season and a dry season. And by definition, monsoons need to have these large cells we were talking about need to be at the crux of why we have our dry and wet season. So here in India, in the winter dry monsoon season, you can see they've got some orographic lifting going on. Now, what's it lifting? It's just lifting dry air from the continent. So this actually would be a dry, warm air that comes down on the other side of the Himalayas. Over here, then, the intertropical convergence zone moves, and now we have this sort of thing where we have warm, moist air coming in, bumping up against the Himalayas, giving us some little bit of orographic lifting there. That moist those moist chunks of air can go ahead and cool down and rain. So we have these 5 ocean gyres, and they are made up of warm currents are in red and the cold currents are in blue. And what makes these ocean currents is just basically large scale winds that are over the oceans. Prevailing winds, and the prevailing winds, and I didn't emphasize this much, but are actually going around oftentimes these semi-permanent highs or semi-permanent lows. El Nino versus La Nina. I'm not sure how I'm going to ask this question yet, but in order to know, and by the way, El Nino and La Nina, a few things, they do affect the entire Earth. But one way to look at them, to isolate what's going on, is to look off of South America, and then this is Indonesia and Australia. So trade winds, trade winds then actually, in the case of an El Nino year, weaken or even sometimes reverse. And so we talked about upwelling, this kind of upwelling off of South America, which brings cool, nutrient-rich water from below. That coolness is shut down, and so it actually gets warm, and we have precipitation here. So that's an El Nino, and it alternates with La Nina. So it's a lot of moisture over here and dry over here. La Nina is the opposite. So here you can kind of see these easterly trade winds, too vigorous, basically. We have too much upwelling. It's cool here and kind of dry, and then these over here, Indonesia and Australia, get all the moisture. Let's see. Hurricanes. I have a question on here, the deadliest hurricane. And it happened a long time ago. Well, I don't know, 1900 seems kind of like a long time. That's a lot of deaths. Okay, in Galveston, Texas, before we started naming them for the alternating female, male alphabetical names. Let's see, anatomy of a hurricane. Generally know the spiral rain bands. Okay, going counterclockwise. Yeah. Okay, around a low. We have a high pressure up here. Here's the eye. Around the eye is clear, but around the eye is the eye wall, which has your intense storms. Outflow is kind of coming out from this high pressure up here going clockwise. Ingredients for a hurricane: you need warm water, so you need to be kind of near the intertropical convergence zone or the equator. but you need enough spin, so if you get too close to the equator, it won't work. So if this is the equator, you can be you have to at least be 5 degrees north or 5 degrees south. It won't work if you're too close to the equator. You also need to have a little bit of instability in your atmosphere, chunks of air wanting to rise. So you need to have some sort of uplifting mechanism. Okay, so kind of the stages of a hurricane start as these easterly waves, at least the ones in our Atlantic Ocean. So they start as kind of easterly waves off of Africa. Then we have these 3 tropical things: disturbance, depression, storm, and cyclone. So kind of know that. They get named when they are a tropical cyclone they get named here tropical storm. Here's where they get their name. So the naming, generally know the rules for naming. They're alphabetical. They alternate male, female. We have some letters that are hard to get, so they're out. If we run out of letters of the alphabet, we go to the Greek alphabet. We actually reuse the list every 6 years, but a name can be retired. How do we categorize hurricanes? Well, we use what's called the Saffir-Simpson scale, and there's category 1, the least, category 5, the most intense hurricane. And these are things that they look at. They look at how low the central low is, how fast the winds are blowing. I have a slide in the next slide to talk about storm surge, and then they're looking to see what sort of damage is happening. Now, a big difference between this and categorizing tornadoes is this is done while the system is active, and tornadoes can only be done after the fact. Something called recurving, which just fascinates me. Recurving basically says that, and it takes advantage of a relative high pressure here in the Atlantic Ocean, so it kind of comes in and goes around. That's recurving. And as it can have all sorts of, say, stages of development as it does that. So, okay. Yeah. Don't worry anything necessarily about these, but I will have a question about storm surge. So here's storm surge down here. Storm surge is where if this is your hurricane is going this way, and you have your most intense things happening right at your eye wall. So storm surge actually occurs as it hits landfall, and it whips water. See, I'm going clockwise. It whips water up onto shore. So your worst storm surge is going to actually be on the right side of the storm. All right, severe weather, last part. So I have in my notes stages of a thunderstorm cell and their characteristics. So you're going to want to know cumulus, mature, and dissipating, but you're going to also kind of know what goes along with each stage. So cumulus is just an updraft. Isn't that a cute little cumulus cloud? It has a cute little updraft. You can kind of see the bottom part. That's the level, lifting condensation level. And this is a mature stage. A mature stage, that's when you're going to get if it's a thunderstorm cell, which is what we're talking about, you're going to get your heavy precipitation, lightning, and possibly hail, and possibly tornadoes. So the thing that's different about the mature stage, it has an updraft and a downdraft. Now, where it's raining, that's actually what we call is associated with the downdraft. And then in the mature stage, we're going to want to know a little bit about hail. Hail actually is a chunk of, this actually says it's a piece of grapple that kind of finds its way down. It catches an updraft, and as it's kind of moving within the cloud, it's getting these sort of layers on it. So it moves up, gets heavy, falls down, catches a bigger updraft, goes up, gets big enough, heavy enough, and it's going to fall down. Okay. And if it if the updraft can't hold it anymore, it's just going to fall all the way down. So you get this hail shaft right here. The last stage after mature is the dissipating stage, and then the thing about the dissipating stage is it's only a downdraft, and it's on its way out, dissipating stage. You're going to want to, you're going to see a figure of sorts and kind of label some things associated with a cumulonimbus cloud. We have these overshooting tops. This actually is the anvil, and the anvil will show you the direction the storm is moving. You can see the updraft in red here, the downdraft in blue. We know it's a downdraft because I have precipitation here. The updraft can make this, actually this is a shelf cloud. I think I have another figure coming up to label these things. A shelf cloud right here. Associated with your downdraft, okay, here's where the precipitation stops, but actually this is just wind. Okay, associated with your downdraft, and it can create what's called a gust front. So you might be sitting here just on your porch, and you get this you got this wind that is like before the rain. That's a gust front. It's being created by the precipitation is creating wind going down and splashing on the ground and heading your way. Kind of fun. Let's see. Of these two multi-cell thunderstorms. Now, the things we just talked about were single cells. A single cell will go through the cumulus and the mature and dissipating stage. But if you get a bunch of them together, there are two types, and I want to talk about the squall line type. So the squall line type is actually associated oftentimes with a cold front or a dry line, which is another type of front, but a cold front. And so if this is a cold front, I'll put triangles here, they would be blue. That actually is causing a lifting mechanism, so we can have this, and if the air is all as moist, it can be unstable such that we can get this band of thunderstorms. We call a squall line of thunderstorms. Thunder, it's created actually because of heat, and it has to do with the electricity or electrons moving, warming up the air so quickly that basically it expands faster than the speed of sound, faster than sound travels, and it will create a sonic boom. That's it. That's thunder. There's also going to be a question on there about heat lightning, because I just think heat lightning is so fun. Heat lightning is when you see it but you don't hear it, and the reason you don't hear it is because you're too far away and the sound dissipates but the light does not. I'm also going to throw on there, let's see, how did I word that? It's parts of thunder, what causes it? Heat lightning, okay. Categorizing tornadoes. Oh, this is my other one that's even a little better. Your overshooting tops, penetrating tops, they mean the same thing. Anvil. These are mammatus clouds. They're not one of the type of 10 main clouds, but they're associated with just the bottom part of an anvil with a cumulonimbus cloud. And here we see this would be your downdraft, okay, updraft, and this is probably has what we call a mesocyclone inside because it has a wall cloud and a tornado dropping down from a wall cloud. All right, so categorizing tornadoes, they are also, well, they're not a 1 to 5, they're a 0 to 5. Interesting. So they are on a different scale as hurricanes. They are in the enhanced Fujita scale, and actually by far most are tame. So most tornadoes are 0 to 3, but actually the only 2% that are violent actually account for 70% of the fatalities. So how do we classify them? We classify them after, when your insurance adjuster gets out there and looks at things, what sort of category of tornado came your way. So they're done after, and then we estimate this wind speed based upon what we observe. And then the last thing is severe weather. Sometimes meteorologists will talk about a hook echo. And a hook echo, I don't know if you can kind of see the hook here. A hook echo actually literally has kind of a little hook feature, and that's where you would expect to find severe weather. Okay. All right. I think that's it. So let me know if you have any questions.